It's dealing with composite wraps, hence the title of this, the evolution of the composite wrap. We have Bart Davis, who will be giving the webinar. Bart applied his first composite wrap on a subsea pipeline back in 1984. So we're proud to have him here. Brings a wealth of knowledge when it comes to these engineered composite wraps. He also does our composite training at our facility or at yours in the field. Also provides all technical assistance and a field supervisor when it comes to the application of these composite wraps. Please, in the comment section, give me your name and your email so that way I can mail out your 1 hour, your 1 CE accredited hour for you. I'd like to get that to you ASAP by the end of the day. And if there's any questions, just put them in there and we'll address them at the end of the webinar. I'm going to hand this over to Bart.
Thank you very much. And I appreciate y'all having me invited into your office. I hope to make this interesting and valuable for everybody. We're going to talk a little bit about the evolution of composite wraps and some of the origins. Then we're going to get into the science, technology, engineering, and math. You might have heard that quite a bit. If you have kids around the house, that's what they're all learning in school these days, along with some other stuff. And then we're going to dive right into the ASME compliant wraps that are used in your industry. And first, just let me define composites. They're really two or more materials that when they're combined, they provide the properties that are greater than the sum of their individual components. So we talk about composites and two or more materials. I also kind of look at our team here at Belzoni Houston as a composite team. So combined, we offer more than what we do individually. So we deal with composites every day. We do a lot of wraps. We do traditional wraps, and then we also do engineered wraps. To be able to do those engineered wraps, we need engineers. So we have a mechanical engineer and a chemical engineer to do the ASME PCC2 design work. And then the training capability that Quinn was talking about. And then also the materials on site. And then we also have our own field service crew, but we also work heavily with a lot of the contractors in the area. So really all the technology, all the math, all the science, all the material that goes behind this, one of the most important components is making sure that the products are installed correctly. And really that's my responsibility. It's everybody's responsibility here at Belzoni Houston, but I take it personally. So you'll hear a lot about the, the proper application side during this presentation. Talk a little bit about the science. So you go on the internet and you try to research something, you get a lot of different opinions, but I try to go for the oldest one. So 6,000 years ago, the Mesopotamians glued wood strips to create plywood. So I really look at that as probably the first combination of materials to end up with something better than just the sum of their parts. But we look into the actual science behind what we know as composite technology today. 1934, you see epoxies, amines starting to be developed. 1935, that's when glass fiber, when Owens Corning kind of mistakenly, it's kind of interesting if you look it up, but they kind of goofed and made some glass fiber and then thought, hey, how can we use this in industry? So there's your matrix, the epoxies, and there's your glass fiber, there's your strength. Then in 1943, that's when some of the bisphenol A epoxy resins, which are really the backbone of where we are today with a lot of our technology that we use. 1952 was when Belzona, the founder of Belzona, Mr. Svensson, he began looking at corrosion protection using mostly zinc-based primers. And then squeezing in there in 1958 and 59, that's when the carbon fiber was developed by a Dr. Bacon and Dr. Shindo. So now we have an even stronger reinforcement component that enters the scene. In 1960, that's when Belzona Super Metal 1111 paste grade. So now what we see is that science moving into technology. So basically you have the raw materials. How are we going to use those? If you'll notice, 6,000 years ago, we started with wood. We went through the different metal ages, but everything was pretty much dig it out of the ground or refine some man-made component and use that in construction technology. So you really didn't see these advanced materials coming in until what happened in the 1930s, 1940s, 1950s. Those were our world wars. So you look at aviation, you look at the need for lighter, stronger materials. And then in 1960s, you get in the late 50s, you get into the space age. So a lot of these products that we're using now were developed really for ballistic missiles, for aircraft, for very strong, lightweight applications. So we look a little closer, kind of define it down into the Houston or Gulf Coast or refining, chemical processing, oil and gas industries, and where we live our every day. And we kind of look at where these composites move through just kind of progressed. So right away, way back in 1970s, you saw a lot of guys out there that were saying, hey, can't we just put some fiberglass on that piece of pipe and do a repair? That worked pretty good. It was fast. They were people that knew how to do glass work. They were usually your painters and your blasters, and they were called in to say, hey, we can't weld on this, can't do any hot work. Let's just patch it up. So you see the traditional FRPs, the fiberglasses, the polyester and vinyl ester. A lot of these guys were also making fiberglass pipe at the time. So in the plants and refineries, you see fiberglass pipe used, and they were used for repair on steel. Later, a little bit later, you saw some of the water activated urethanes. So same thing, a real fast pipe repair, something that could restore service in an awful hurry. Where did these products lack, though? They really lacked in, number one, their strength for adding additional hoop strength to the pipe, but then they also lacked in some of their bond capabilities. So while they were able to make short-term repairs, there was no really way to quantify the capabilities of those products or to really trust them for any kind of long-term applications. So they were simply used as quick patch application. Also in the pipeline world, you saw manufactured coils. So these were, like a fiberglass surfboard wound up in a coil that was glued with an cyanoacrylate adhesive to the pipeline itself. So a rigid coil was good for a straight run of pipe, but not used so much in our plant and refinery side because of all of the different piping configurations and then all of the aggressive chemicals that were deployed. So at the same time, what you saw was Belzona doing a lot of, and other epoxy manufacturers doing a lot of repairs with the Belzona products. Belzona developed very high bond strength materials, also branched out tremendously from the 1111 into abrasive resistant materials, chemically resistant compounds with a lot of testing and a lot of field applications for those. Not all of those applications, because many of them are used in liners and many of them used as, say, coatings on a containment area. But when we got into pipe repair with those epoxy resins, they were often reinforced with fiberglass. So we still do a ton of those. I would say that probably 30, maybe 70% of our repairs, of our composite wraps out there are still traditional fiberglass type reinforced repairs using one of our epoxy resin systems. These are usually used on lower risk applications or lower temperature and lots of times on chemical service, but where there's not a need for a long-term engineered wrap. The longer term applications require a little bit more of design. They require the engineering. So then that's where we begin to combine carbon fiber with these epoxy resin systems. Fortunately, we have so many different materials for chemical resistance that we're able to combine some of our traditional repairs and filler materials and in the traditional side of the epoxy resin, and then come over top of those with the carbon fiber to be able to develop an engineered wrap. Show you a couple just applications quickly, and then we'll kind of get back into the, well, we covered the science and technology, so we still have the engineering and math to go. Example of modern day composite wraps. So here's just a cooling tower mist. We've all seen these before. As with any adhesive, surface preparation is critical. In this application, you're looking at an area where the wall thickness was 0.170, so that area was blanked out and the rest of the area was properly surface prepared, and then that area became the defect. So with engineered repairs, you're not only looking at structural reinforcement, but you're looking at the ability to stop leaks as well. This application on a leaking vessel nozzle, this was actually on an offshore production platform, was designed for a super wrap repair. What you're seeing here is pictures from the initial assessment. And then on the right, these are little screenshots that we pulled out of some of the design work that Alex Zamsis does for us. He's our chemical engineer that does all the designs to PCC2. So there's some of the actual repairs from this particular repair, or actual photos from this particular repair that shows kind of a before and an after. So what I was talking about combining the materials of traditional resins and then reinforcing that with, in this case, a Super Wrap 2, the engineered composite. So on the picture on the left, you can see where a paste grade was used. So that would be a fast setting, leak stopping type composite material that was applied to stop that. And then on the right where the whole thing was reinforced. And next we're looking at some composite patches on some storage tanks. So we'll get into a second into some of the standards, but API 653 does allow for carbon fiber repairs on storage tanks. So it's a very popular application for Belzona. I would say we probably work better than most of the repairs out there because everybody can design it, everybody can come up with a material to address flat patchwork. But just from my field experience, I can tell you that our stuff is tacky. So it has the high adhesive bond, but it also has a tackiness to it that allows it to work on vertical surfaces. Belzona is good at making adhesives, and we've got some good ones that we can use. So as we get kind of closer, inching in on the PCC2 Article 401 code, we talk about engineered composite repairs. And what this code does, it's applicable for pressure vessels, for piping, for tanks. It prevents corrosion of the substrate. So if you're looking at a problem with external corrosion, a lot of these products are based on corrosion inhibiting technology. So you stop the mechanism that caused the failure if you're looking at external repairs. There are internal applications where we're looking at through wall defects from internal erosion. And in that case, you are designing those to what we call a type B repair. So you can design those to a certain length of time. Normally, the external repairs are designed to 20-year lifespans maximum. The internal repairs, we kind of look at how big of a hole could grow based on the erosion rate, could grow underneath the composite before it's too large for the composite to handle that load anymore. So those are normally fairly temporary type applications. All these repairs, not all of them, but a big chunk of them are done with the asset in service. Lots of times when we're using our higher temperature resins, the asset is actually used to post cure the material. This particular repair on this tower is still in service. They have a turnaround coming in next year. So it's been inspected several times, and it's still rocking and rolling. So that's a kind of little bit larger application. We do a lot of vessels, do a lot of tanks. A lot of what we do is more spot type repairs, but I know we'd have a fairly large vessel wrap going on as we speak with some of our technicians. So as I promised, we kind of went through the science and technology. So let's kind of get into the engineering and math a little bit. You're talking to the field consultant guy now, or he's talking to you. So I've been involved with these engineered repairs ever since the standard was written. I've served on committees. But if we get into running some of the calculations, that's Alex's job. But I can do it kind of just a brief explanation of how that works. What you do is you basically bring to us your problems. So you're filling out information that gives us the diameter, the pressure, the service, information about the defect that you have, as much of the NDT information as you can supply to us. We also, when we get into some of the piping, we need to know what the SMICE, or specified minimum yield strength of the pipe. And then what we're going to do is we're going to determine how much material needs to be applied and a thickness and a length to be able to bring that pipe back up to its original pressure handling capability. So a lot of that has to do with the bond strength, and the bond strength has to do with surface preparation. So at Belzona, what we've done is we just haven't said, hey, let's blast everything like they do in the pipeline world and let's test a blasted pipe. We really look more at pipe that's prepared using power tools as well. So API 570 would be your inspection for the piping systems. API 570 looks at a composite repair the same as a engineered clamp that a leak sealing company would put on. So it's considered to be a kind of long-term temporary repair. API 653 allows for the repair using composites. That's only about 2 years old into that API 653. And there are several, there's an annex that you use that takes the requirements of PCC2 and adds some additional requirements that you have to consider, or considerations during the design of the repair. So you just go in, and what you're doing is you're looking at your, you plug it in the data from your, the performance testing of your materials. And it is plugging those into formulas. And then what it does is it comes out and finally spits out your design. So we try to make it, these designs easily readable by the person that's going to put them on, the contractor or our own group. We do a lot of training that's specific for repairs. So we'll come in even after the training, we'll get together with whoever that field service crew is and make sure they understand all the steps to the repair. I don't know if you can really see it, but this particular one has a plate bond underneath it. So there was a bonded plate that was put in place over top of leak using Belzona, and then it was structurally reinforced with the Super Wrap 2 carbon fiber material. And this particular one was a 6-layer application. Had a leak at the weld on the left, but the entire area was considered defective and had a potential for leaks. So the entire elbow was wrapped. Training's a big part of it. That's what I do. We teach this classroom, the theory, the safety, how to keep records. That's a big part of it. You want to know that this product has been applied correctly. So we do a lot of hands-on training. We look at a lot of different configuration, and then we hydrostatically test a spool piece from each one of these, each crew or each several individuals during a class. So it's basically like a welding test. You know, these guys have a pass-fail where they have to seal a leak. That leak is a 3/8 inch hole. It's on a 4-inch spool piece. They have to pass 1,500 PSI. Typically, we get to 1,800 to 2,000 PSI with a 3-wrap 6-layer system. As I talked to you or just mentioned earlier, record keeping is a lot of what we teach. So we make sure that for ISO compliance that we're following our batch numbers, that we take the environmental readings so we're within the parameters of our products, that we're doing a surface preparation that was called out for in the design. Basically, all this information is what good coatings people, it comes from our kind of our heritage and our mindset of being coatings people first, to make sure that all that QA QC is done, and then tracking the training that's required in ASME PCC2 with the individuals and make sure they're still qualified to apply the material. And we can certify these repairs basically for fitness of service. We have material scientists and engineers back in our corporate office in Miami and Belzona that can certify a lot of these repairs and basically put an inspection interval on those. Just a few more applications. Here's a stainless steel tank on the inside. Our guys love to crawl through those little 20-inch manways and get inside the tanks. So here's one I mentioned. It's the tackiness of the material. We'll also use magnets. We use salvage magnets when we're, say, on the outside of a steel tank. These are extremely strong magnets that we'll put on each side of the repair. Then we'll put a backer board over top of the repair on a flat surface, and then we'll run straps across that. So we have a mechanical way to compress the repair into the surface while it's curing. Here you see the compression film that's been wrapped around a line where we already repaired the nozzles, wrapped those, and then we came in and consolidated that with the remainder of the piping. Some of our repairs are not compliant, so to speak. Some of them are our best effort. In this case, what looks on the left like like a snake that ate a Nutri-Rat, and that's because there's a repair clamp underneath that. So this was a leak and repair clamp. They asked us to come in and wrap over top of that clamp. Just not able to design a compliant repair, but still something that gave the customer more confidence in that whole repair scenario. And we treated it in the same loving way that we do everything else, with all of the design parameters and the training. Leaking nozzle, I think we showed you that one already. And then we do some fiberglass piping too. We just did one of these offshore that we actually took someone else's wrap off and put ours over top of it because it had failed. So we have a lot of different materials. The standard is written for metallic piping. So we're doing Monel, we're doing stainless, we're doing carbon steel. It's not written for fiberglass, but the products are very effective on fiberglass. And lots of times we're doing a more traditional wrap. So this shows one of our traditional wrap products using our 4151 resin with a 5111 overcoat on top. So this is just more of a traditional repair. One of the other things that we do is, you can't wrap something on the inside of a pipe, and you have a crack in a nozzle interface with the vessel. So we manufacture a nozzle insert. So what we're able to do is we can make this out of carbon fiber, we can make this out of fiberglass, but normally what we're doing is we're making it out of a Belzona product that is resistant to whatever the service is, whatever the chemical is in that line, and we're inserting that nozzle into the inside. It's really an easy way to coat and reinforce a pipe from the inside. Here we are making a nozzle insert in our shop for this application out of the carbon fiber product or out of the composite material. Also,
It's
there's
going to be closed, period.
Pardon me? Okay. So really, if you look at, the future of composites, I'd say we're just kind of lighting the rocket right now. You hear about nanotechnology, extremely lightweight, super strong. You've got composites that can change their physical properties on demand. They're already out there where you can, tell your window to darken up and it'll darken up. I think we're not completely beyond the fight with people that prefer, welded technology or steel for everything. But those same people, have a carbon fiber driver in their golf bag. They get on a airplane made out of carbon fiber. So whether they're accepting the technology or not, the technology is right in their hands and they're sitting in it. So it's really come a long way, and we're proud to be a part of it. So that's all I've got for today. Happy to answer any questions. We're always here. We're 24/7 people because like I said, we work in this industry. We also have 12 reps that span from Lake Charles down to Bay City, which is within our territory, and then the entire Gulf of Mexico, and then up into the paper industry up in Shreveport. So, and northern Louisiana, Texarkana, that area. So what's really good about that is you've got 12 pairs of eyes. There's one assigned to your account, whether you know it or not, or whether you want him or not, but he's there to come out and take a look at what's going on. So we don't do all this by the phone. You can't install a composite via a webinar. You got to send men out and women out to do it. But we really like to get our eyes on the asset. We don't want to find out that you can't do the surface preparation required after we've designed the repair. We want to talk to you about, do we have to use sparkless grinders? Do we have to, what are the parameters? So we deal right in that plant and refinery world every single day, and we're realists. So we know the challenges that you're working with, and we're going to try to make composites work for you. If they can't, we'll tell you no.
Thank you, Bart. Thank you, everybody, for joining and getting me your email addresses as well. We'll get this credit hour to you. I hope you're able to find some good value in this on our engineered composite wraps. As I said, this is a recording, so it will be sent out to you. You can also find it on YouTube. Again, thank you, Bart, for that. Very knowledgeable. And everybody for attending and taking some time out of your day.
Thank you.
Everybody still left and has some questions, I'm hanging around. We only got 3 designs to do today.
Good job, Bart. Enjoyed it.
Thank you.